In popular conversation, discussions of data visualization often invoke examples such as these. Custom, bespoke graphics, often intended to convey a story, and handcrafted by skilled visualization designers. And so over my years working in visualization research, my students and I have sought to create tools that enable these kinds of sophisticated graphics, giving rise to popular tools that we've developed, such as ProtoViz, Vega, and D3. And while we've been very happy with the success these tools have had, I think they're only a small part of the larger ecosystem of visualizations. Because if you think more broadly, the vast majority of visualizations are not hand-coded, but rather built with end-user tools, often leading to visualizations that look like this, or applications that look like this. And while well-intentioned, many of today's end-user tools either have lack consideration of perceptual principles or fall short of fully supporting the process of visual analysis and exploration. And so when I think about the future of data visualization and how we chart a path forward, one consideration to think about is how do we move from tools that work well from designers to tools that really enable analysis and decision makers to advance their causes, to enable better decision making across industry and government, for example. So how can we advance the state of the art? Well, I think one way is to begin to bake more design smarts into our visualization tools. And to give you a sense of what I mean, let's just conduct a quick experiment. I'll show you some shapes. I want you to compare them. Don't yell out the answer. We'll take a quick poll on your response. So here's two circles, and I want you to compare their area. How much larger is the larger circle than the smaller circle? So raise your hand if you think the big circle is 4 times bigger. So you want to take a look around. Okay, 5, 6, 7, 8, 9, 10. A lot of people. 11 or more. So there's others. Okay, then now let's try another example. Compare the length of these two bars. How much larger is the big bar than the smaller? Raise your hand if you think it's 4 times bigger. No one. 5, 6, some more, 7, even more, 8, a lot of you, 9, much fewer, 10, 11 or more, almost no one. So it turns out the answer in both cases is the same. It's 7 times larger. But if you looked around the room, what you've noticed is that despite the same difference in areas, they were actually much more accurate and less variance overall for comparing length than area. And while this was hardly a scientific poll, my group and others have conducted experiments like this in controlled settings to compare the accuracy of different encodings. So for example, you see error rates comparing things such as position, length, angle, and area. And by combining the results of these experiments, we can actually build rankings of visual effectiveness for different encodings for different types of perceptual tasks. So for example, when comparing quantities, position and length outperforms things like angle and area, which roundly outperform color encodings. And this is useful to help guide, though not dictate, what human designers do, but also very helpful for guiding algorithms who might automatically recommend effective and useful graphics. So for example, at Trifacta, our product includes support for visual profiling of large data sets. Here we see a visualization of a geographic field showing where political contributions come from, right now using a common color encoding across states. Do you notice the problem? Well, as we just discussed, color is one of the least accurate encoding channels for comparing quantitative data. But I'd argue there's an even larger problem with this graphic, which is our perception of value is correlated with the size and shape of the states themselves. So we can't even see what's happening in Washington, D.C., which, as it turns out, is a source of many contributions. So what other visual encodings might we consider? So for example, we'd like to maintain the spatial context of the map, so position's already spoken for, but we could move to something more accurate like area to enable more effective comparisons. But as I also mentioned, position is one of the most effective encodings, so we also augment this display with bar charts on the left, so we can make comparisons in that way, and then link these views together through interaction, thus enabling more exploration, allowing us to see more patterns, and make comparisons more accurately. So baking in better design smarts into our tools, I think, is one way we move forward, but it's just a beginning. I think more broadly, it's time to rethink some of our basic user interfaces for data visualization. For example, most tools involve a process of, specifying charts. How do we move this to a richer process of rapid exploration? So common end-user tools will have us select data subsets that we're interested in, and then choose from a set of chart types or specific visual encodings to manually build up a display. But this can be overtly tedious, but it also seems like there's a lost opportunity to recommend interesting views. So for example, in the Trifacta Visual Profiler, we don't have people build charts explicitly, we provide them. So on the left, for example, you see overviews, where we automatically present summaries of all the dimensions within a data set, but then users can then drill down for more detail. So for example, this panel on the right is showing when political contributions occur. And this is shown both as an overall timeline, as well as summary displays for time periods, such as day of week or month, day of month, etc. And doing this, we can see a number of patterns. We see that contributions are more likely. They occur with increasing regularity as we get near an election. And they're also more likely on weekdays or at the end of a month. So we learn something useful immediately without having to specify the charts. But probably the most important point here is that these displays were chosen automatically based on the data. So for example, there's very little variation amongst things like hours, minutes, and seconds. So we don't show those charts to avoid distracting the user or wasting their time. Simultaneously, over in my interactive data lab at the University of Washington, we're exploring new end-user exploration tools. So for example, our Data Voyager system actually searches over a space of thousands of visualizations and ranks them according to statistical and perceptual measures to provide recommended visualizations for a data set. And of course, the user's in the loop as well. So for example, you can steer the recommendations and update display based on indicating fields of interest. So again, trying to change the way we interact and explore with data to enable a broader and more rapid exploration. So there's a lot of challenges that come up in moving from specification to exploration that I'm not covering. And to do this well actually requires the combined talents of the Strata community, drawing on visualization design, statistics and machine learning, as well as big data systems. So I'm very excited about the challenges that are presented to us, but I also think we have to consider the ways in which these tools will really augment analysis in the most productive ways. And so to illustrate that, I'd like to share with you a data set that I often give to students in my visualization course. This is a classic data set originally published in the 1950s, comparing the effectiveness of antibiotics, which were at the time new wonder drugs, against a variety of bacterial strains. So I give this data set to the students and ask them to explore the data, create a graphic that answers an interesting question. So here's some of the student submissions. And already you can see the great variety in designs that they explore. So that's at first really interesting. But one thing that pops out as you start to dig in and you really inspect these graphics, you realize that while they have lots of design variation, they're actually all addressing the exact same question. Which antibiotic should one use? And so this fixation on this one question reminds me of one of my favorite maxims from the visualization expert Edward Tufte, who advises us to show data variation, not just design variation. So the idea is that while it can be useful to explore multiple representations of the same subset of data, it's often even more vital to explore different slices and transformations of the data that might spur new questions or address different hypotheses. Or rephrasing this, I think we should consider how might our tools better spur us to exercise skepticism about data and consider new questions. So, consider this alternative visualization. It's fairly simple. What we're seeing is the different bacteria in a scatter plot. The bacteria are colored by genus, and they're plotted according to the effectiveness of two antibiotics, neomycin and penicillin. In this case, the lower left corner is areas of very high resistance, and then the upper right corner will be areas of very low resistance. And the idea here is that just by suggesting this relatively simple visualization, we may still be prompted to consider other questions. By putting the bacteria front and center, for example, we might ask instead, what does antibiotic response reveal about the biology of bacteria? Sort of flipping the question. If we look back at this chart, you might have noticed something interesting, that there are different clusters of bacteria, but they span genus in perhaps surprising ways. Like, wouldn't bacteria of the same family be more likely to group together? Well, you'd be right to be skeptical here because there's actually errors in the data. The scientific community was originally wrong and has two misclassifications in this data set. And so it actually took multiple decades after the original publication of this data for the scientific establishment to overturn these errors. And yet, the initial evidence was here all along if we had thought to look at the data, through this particular lens. So it's interesting to think how our tools might prompt us to consider our data more broadly. And so as we move from specification to exploration, we should also keep in mind how this best enables analysis. For example, enabling data variation over design variation. And so, in conclusion, I'd like to look forward to a future in which our tools don't just help us build visualizations, but help us much more richly explore the data, in the end, hopefully leading to better insights and better decisions. And so now I look forward to all of us, building this future together. Thank you.